Hello everyone, my name is Clara Gonçalves and I'm the Vice President for Partnerships of ENSICO. ENSICO is a non-profit organization that defends a mandatory discipline of computer science for all students of basic and secondary education, Key 12, by proposing a program and the curricular goals that promote digital literacy and ethics based on the fields of computer science. Today, we are launching our first conference, Living with Technology, Innovation in Education, within the scope of the project Computer Science for All, funded by Erasmus Plus program. We will have a strong panel of experts in the fields of computer science and education, and the conference will be focused on 3 pillars. The first one will address the perspective of the computer science scientific community. The second one will address what should be the best curriculum design, what kind of knowledge, skills, attitudes, and values are needed within the scope of education and computer science to understand a changing world towards a better future, of course. And the third one, the social and economic perspective, will allow the participants to have a broad perspective about the framework being built, involving different experts and interactions within universities, industry, government, foundation, as well as understanding how policies and practices can be transformed effectively to support the next generation of teachers and educators. According with the last-minute update, the conference has 302 attendees, most of them online. We tried, from Brazil, United States, Italy, Angola, UK, and Portugal, with a broad scope of people coming from corporate companies, startups, universities and polytechnical schools, NGOs, municipalities, national funding agencies, and of course, teachers from primary to secondary schools. Before giving the word to our host, Professor Falcão e Cunha, Dean of the Faculty of Engineering of the University of Porto, which we deeply thank for all the support as a host, I would also like to thank to our partners from Erasmus Plus, the Municipality of Porto, InCode 2030, Fundação Carlos Gulbenkian, Jornal Público, and SONAI. One last thankful word goes to the incredible partnership and support established with APDC. Thank you, Professor Rogério Carapuça, Sandra Fazenda, and all the dedicated and happy team with who we worked for the past weeks. And ENSICO, we are very proud to say this, ENSICO has at this moment the high patronage of the President of the Portuguese Republic. And it's a huge, huge pleasure that I call Professor Falcão e Cunha to open this event. Thank you.
Good morning, ladies and gentlemen. I renamed the colleagues that Clara introduced, so thank you very much for being here. Thank you very much for not being here, but being with us online. I'm very happy to host here this event. And of course, I'm also from computer science. My background was in this area. And so I share, of course, the relevance of this program, of these objectives. But I would say that I was telling Clara before this that according to Seymour Papert, Papert was the inventor of Logo language, and he was a student of Piaget. I heard him once saying that we don't need a course for kids in computing or in computer science. We need that all courses involve computer science or involve computer technologies or involve computer tools. And that's a big challenge because sometimes kids know more than their professors. And I usually told my students when I was teaching that if they don't know more at the end of the course than I do in some aspects, I failed in that course. So I hope that this conference, this event will be very successful and that we will learn something important, or you will learn, because I'm going to, I will need to go away soon, but that we will learn something important that changes our lives, and more important, that changes lives of the young people, that will make them better persons, and that will influence the society, so the society will become a better society. So thank you very much for the initiative. I hope you will also not only learn but enjoy it, and hopefully next time we'll have this small seminar room full of people, and we can have a coffee break, or 2 coffee breaks, or 3 coffee breaks, because the coffee break, if there is one, I don't know, is there one? Okay, so it's only for the people who are here, but I suggest that if you are away, you also should have a coffee break when we are having a coffee break, or better, you could have some champagne in the afternoon or something else. So thank you very much, and enjoy and learn. Thank you very much.
Morning, everyone. I would like, first of all, on behalf of APDC, the Portuguese Association of Digital Companies, I would like to greet our partners in this event, ENSICO and the College of Engineering at the University of Porto, for the great partnership we have been developing and starting, I hope, with this conference and with many more events. So just brief words to open this conference. Digital transformation is changing everything in our lives. It's changing the way we work, it's changing the way we do business, it's changing the way we learn, the way we communicate with each other, and should as well, and is as well, changing the way we learn and the way we teach. But we have to think that digital transformation is in fact to change the processes by which things are really done. And in education, education has been very much stable during the last, I would say, centuries. Since the last technology revolution before computers that was relevant for this field, which was the invention of the press back in the 1430s. So basically, after that, people have been taught and people have been learning more or less the same way. So we should rock the foundations of this building. We should not only bring some gadgets in order to be able to learn in a slightly different way, by producing content in a slightly different way, but we should rock the foundations of this building. And that means to insert the computational thinking, for example, which is the topic of this conference, into our K-12 curriculum. Because that will be useful not only to understand how computers work, but to understand which are the good strategies to solve some problems in any field. So, because the basic building blocks will be the same. We should divide problems into smaller parts in order to be able to solve them better. We should be able to know how to generalize, how to pattern recognize things, how to make pattern recognition. So there are some building blocks that we need to understand how we do things in order that we can learn better, in order that we can practice better in many fields, in, I would say, all the fields. So I think this conference is really about that, is how do we do that? If we agree that we need to do that, we should do that, and how and when should we do this kind of things in our own K-12 curriculum. So that's why we are here. And of course, we should also understand and try to learn with other partners, with other countries that have already done that for several years. How do we establish this? How we gather all the stakeholders that are needed in order to make this transformation? Because it is not only important to explain what this transformation is all about, we have to figure out how we change. And changing in education is hard. So how do we get all the stakeholders involved in this, and what kind of process do we build to change this? And maybe some computational thinking can also help us to figure out what algorithm should we use in order to change this. So I think this is the topic of our conference. I hope we can learn from it, and I hope that everybody, including those who are online, can participate and profit from this event. Thank you very much.
Our first session will have a very special keynote. Simon Peyton Jones. Simon is a British computer scientist, graduated from Trinity College, Cambridge in 1980. He spent 7 years as a lecturer at University College of London and 9 years as a professor at Glasgow University before moving to Microsoft Research at Cambridge in 1998. He's now an engineering fellow of Epic Games. I think everyone knows what is Epic Games. Simon's main research interest is in functional programming languages, their implementation and their application. In 2016, he was elected a Fellow of the Royal Society and a Distinguished Fellow of the British Computer Science in 2017. But the main reason Simon is today with us is because he's the founder and chairman of the Board of Computing at School, an organization which aims to promote the teaching of computer science at school. Following these efforts, in 2019, he was appointed chair of the newly founded UK National Centre for Computing Education, and is also widely seen as the most energetic, enthusiastic advocate of school-level computer science education in United Kingdom. Simon will talk us about the power of computational thinking. Simon, good morning, and thank you for being with us today.
So it's a great honor to be with you. Thank you for inviting me. In the next half hour, I'm just going to share a little bit about the journey that we've been on in the UK, and also a little bit about the symbiosis between maths and computing education, which is something that's, I think, particularly important in Portugal, as I understand it, at the moment. So here's a good place to start. Richard Riley was the Secretary of Education in the USA, and he said, education should prepare young people for jobs that do not exist, using technologies that have not yet been invented to solve problems of which we are not yet aware. I love the aspirational sense of that. How do we go about educating our children with that level of aspiration? Well, the answer is we teach them something about subject disciplines and something about applied skills. And by disciplines, I mean words like ideas, knowledge, principles, methods, and techniques in subjects like maths or science. And by skills, I usually mean something to do with devices, artifacts, programs, and products, tangible things, and the skill is the ability to use them in an effective and disciplined way. And schools typically teach both of these things in all subjects. That's our aspiration. Along the discipline side, you might think of disciplines as being concerned with ideas, with creating things, with being an author, with writing. And on the skills side, you might think more about technology and about reading rather than writing, about consuming rather than creating, about using rather than understanding. And this is not to downplay technology. It's super important, and it's fantastically important to be good at using these devices. But if our children come to believe that the sleek devices they use are essentially magic, and I'm quoting Arthur C. Clarke's famous third law here, then they have no power over them. They're reduced to uttering spells that make them do what they want. If they have underlying knowledge about how these things work, that gives them power over the magic. And I think that's our goal here. So in England, at least, in the mid-2000s, the situation was we had a subject called Information and Communication Technology that was the right-hand side of this slide. And look there, technology was right there in the title of the subject. And we didn't even recognize that underlying it was a subject discipline of computer science. At least we didn't recognize that at school level. It was essentially an exclusively skill-led subject. So the obvious thing to do is to try to rebalance our curriculum to have a proper balance between the discipline of computer science or informatics and the digital skills that make it useful in the real world. And I think that is a vision that you have now embraced in Portugal. So this conversation for me, just to share a little bit about the journey we've been on in this country, began when I was talking with my children about ICT, which they were then studying at school at the time, and they were not keen on it. They were almost contemptuous about it. So with others, including Simon Humphreys, who you will be hearing from in the very next session, we founded this organization called Computing at School that was very much a grassroots, bottom-up, volunteer-led organization that tried to change the weather of what a computing education might look like. So there was a great deal of paddling under the water, but we established very early on this vision for what we thought computing education should look like. And I think this is a vision, as I understand it from Miguel and his colleagues, this is a vision that you in Portugal have fully embraced, that all children should learn computer science as a foundational discipline, just as they do maths and natural science, and should do so from primary school onwards. And here I'm stressing every child. This is not just the future software developers. It's not just the boys. It's not just the middle-class children. It's everybody. And why is it everybody? Because we teach science, natural science, to everybody, not because they are going to become the physicists of the future, though some of them will, but because you can only make well-informed, evidence-based judgments about your life as a citizen, or what your country should do, or what you should do, if you understand something about the natural world that surrounds you. And in just the same way, I think that our children will only be able to make well-informed choices and have agency in the digital world that surrounds them if they have underpinning foundational knowledge, just in the same way as they do for natural science. So that was the vision that we established for computing at school, and it became enshrined in the national curriculum. Here are the 4 aims of the national curriculum, which was launched in 2014. And you can see that right up there, this covers from age 6 through to 16. It says, in black and white, all children should be able to understand and apply the fundamental principles of computer science. I'm very proud of our country's enshrining this in black and white in the national curriculum for our country. Turning it into reality is a different matter, but at least we say this is what we want to do. And I think this is the vision that you have embraced as well. This did not happen quickly, right? This took, we're now, let's see, 14 years into this change, and we're still working on it. So in education, nothing happens fast, but it does happen. It can happen, and I believe it is happening in your country as well as ours. So I will not pause on the history here because I'm keen to get to the content, but I will just pause to say that as well as launching the national curriculum, it's the new, trying to ask existing schools and school teachers to teach a brand new subject discipline that there's never been taught at school before, that is computer science, particularly at primary school, is a huge request that we are making of them. And now recognizing that challenge, the UK's government has launched the National Centre for Computing Education, whose main purpose is to support the professional development of computing teachers to teach the most fascinating and creative and economically important subject on the face of the planet. This is, as Miguel was put it, rocking the foundations of the building. There's a long way to go still, but at least we have the National Centre, and it is, I believe, having a big effect on the lives of school teachers. All of its resources, there's a URL on this slide, all of its resources are under open government license and available to you just as much as you like. You can use them, they're available in soft copy, you can repurpose them, you can rewrite them, you can translate them into Portuguese, you can do whatever you like with them. Okay, so as I understand it from talking to Miguel and his colleague in Portugal, you're engaged on this journey as well, and actually have a pilot project started with, I think there's 1,000 odd students doing this, in close cooperation with the Ministry of Education, through the means of adding computational thinking to mathematics education. Now that is a different path than we took in the UK. So in the UK we had this subject called ICT that was already had its place in the timetable, and we've simply rebalanced ICT. You're instead adding computational thinking and computer science to mathematics. So I think there's a lot to be said for that. I want to say a little bit more about that in the main payload of this talk. But I think the good things that you're doing is running, rather than just doing a big national policy change, you're running a pilot. What a good idea. Let's try things out. As I understand it, teachers are playing a leading role, and that's really good. And the Ministry of Education. So if there's any people from the Ministry of Education here, thank you so much for coming to this conference. And we really need you as partners in this journey, because we can only do a good job of this if everybody from teachers up through the Minister for Education are working hard in the same direction to try to give our children a good education in computing. So let me just say a bit about what I feel the opportunity of combining maths and computing is. So in England, we've now positioned computing as a foundational subject. In Portugal, you're introducing it through mathematics. So, but in both countries, I think here's a good question. How could we take the symbiosis between mathematics and computing from aspiration to reality? And by symbiosis, I mean, I've given a dictionary definition here, living together, a close and long-term interaction between two different biological organisms. So here it's computer science and mathematics that are sort of different subjects at university, but they are, I believe, symbiotic, and they can live together in a way that benefits both. So the unifying idea I'd like to suggest to you is that computing, and computer science in particular, is mathematics made incarnate. That is, it takes flesh. It makes mathematics tangible. It makes it executable. It makes it concrete. It makes it playful and experimental and exploratory. And often it provides a motivational context for mathematics as well, rather than just solving simultaneous equations. You can say, well, we want to make, the lunar lander hit the moon at the right time. So here's a little example on the right-hand side of the slide. Well, here's a little for loop. It's an executable program. You can run it and see what it does. But like an inductive proof in mathematics, it has a base case in which we initialize the sum. It has an inductive step in which we we add I to the sum. There's even a theorem about it that is the loop invariant that says after j iterations, sum contains whatever it is, the sum of the numbers from 1 to j. And then you can use an inductive proof to show that that loop invariant holds. Now, this is a relatively sophisticated example, but I like the way that there's such a close connection between the idea of an inductive proof, and which is quite abstract and students find it hard to get hold of, and an executable program that's a for loop that children will learn when they're 8. So, here's a little illustration of what I hope we might achieve. Right? This is a story of Miles Berry, who is the gentleman in this slide, who's I think many of you will know. And he was giving a workshop about Scratch programming in London. And in this workshop, one young woman that he was with, who was a primary school child, realized that she could replace this sequence of 8 turtle graphics commands with a for loop with only 2 turtle graphics commands in it that were executed 4 times by the loop. And nobody told her this. She just saw the for loop in the palette and guessed what it would do and tried it out. And it worked, and she explained it to her group, and she went away happy. But what I particularly liked was this email that her school teacher sent to Miles a few weeks later. He said, "Here I have M. Self-esteem going through the roof. She has associated this computing success with mathematics. Over the last couple of weeks, she's solved maths problem after problem at target after target. She's truly flying. She is going great because of a positive experience in a computing workshop in London." And so somehow this experience that she had gave her agency, confidence, ability in mathematics that she didn't feel that she had before. And I think that is really exciting. This warms my heart. This is what I feel we are, the enterprise that we are all engaged in. Okay, so those are the positives. Let me just say a couple of dangers that I think you will probably be thinking about as you introduce computational thinking into your maths curriculum. The first is that we might perceive mathematics and computer science as in competition for limited time. So there's a kind of zero-sum game going on, that anything you give to computing, you take from mathematics, right? And so we're living in silos, and we can only win if the other guy loses. That, I think, is a serious danger that we must try hard to avoid. And it's because I think that actually, as I've been saying, I think mathematics and computing education can enrich and inform each other. So we can both be better off if we do this mixture, right? 1 and 1 make 3. Second danger. Computing, of course, is fashionable, right? Politicians like talking about it. It's the Facebook is all in the cyberspace and the internet and the metaverse. It's all over everywhere, right? So schools like to have something about computing in their curriculum, and so do ministries of education. But the danger is that computing is perceived really as a sort of useful decoration for real mathematics, right? So here in my picture, the big buffalo is real mathematics, and computing is the little symbiotic bird that pecks the fleas off the back of the mathematicians, right? But I think we need to go beyond this. We need to go beyond looking good to really trying to see how computing could improve and change the teaching of mathematics, and vice versa too. So not just a way to do maths better, but a way to do better maths. That is our goal here. Okay, quick digression. I do want to say some things I'm not talking about. So one thing is that computing is useful as a teaching aid, right? To teach history better, to teach geography better, to teach English better, right? And that is super important, that we can teach every subject better using information and communication technology. That is important, but it's not what I'm talking about. I don't think it's what the subject of this conference is. But don't let's mix them up. And another question, just going back to my previous slide, not just a way to do maths better, Conwell Wilson has a very persuasive story about how it's silly to teach mathematics as if computers didn't exist, right? We should use computational tools to support the teaching of mathematics, and we should, right? And that too is not my focus, though it's about the symbiosis, so that's what I'm after. Let me say very briefly what I'm thinking of when I talk about computing or computer science. What am I really thinking of, and what themes are shared between that subject and mathematics? Well, so I think of computing as the study of information, computation, and communication. Notice, not a study of data, algorithms, and networks. Those are, as it were, applications of those underlying set of ideas and subject disciplines. And programming sort of infuses all of it. Programming isn't like a separate subject. Programming is everywhere in all of these topics. I think sometimes we get a bit focused on computing as a study of computation, that is algorithms and programming, and we don't think enough about communication, and we don't think enough about information and data representation. Though with the emphasis on AI and data science, we're getting more emphasis on information coming through. And there are lots of common themes, right? So abstraction is a key principle in computer science, but it's also all over mathematics. Often not by that name, but in every maths problem, we go through the process of saying, we want to see when the car gets to Manchester, so we need to make some abstraction. We don't need to think about what color the car is. We don't need to think of what the air resistance, because we're going, that's relevant, but it's too small a variable, right? We want to think about the speed the car goes and the distances, right? So we abstract from the real world to something that we model. We then do some intellectual thinking about that, or in computational terms, we do some computation about that. But in mathematics, we might do some algebra about it, and then we map back to the real world. All of that is completely common to mathematics and computer science. Other common things is we encourage precision in thinking, right? And we great precision in thinking. In fact, computers are rather pitiless about that. So I think there's a lot of stuff in common. Now, of course, we're not the first people to say, maths and computing have a lot in common. There's lots to draw on here. Let me just very briefly mention 3 projects you might want to take a look at. I'm sure some of you are. The UCL Scratch Math projects had this lovely statement on their opening page. Mathematics is difficult, but in part because of the language in which it is expressed. Can we find a different language set of ideas and approaches that is more open and accessible and more learnable through the medium of computing? And their answer is yes to this. And it's a really good project. They have lots of resources that would be very useful to teachers in Portugal as well. I've just picked out from their opening video these little stills. This young woman who said, what we really like about Scratch is when you press that start button, it's like magic in front of your eyes. Isn't that a lovely statement? Wouldn't you like maths teachers? Wouldn't maths teachers love their students to be saying, it's like magic in front of our eyes? Bootstrap World is another project, this is based in America actually, that has explicitly teaches mathematics through the medium of computing. And Paul Curzon, who many of you will know, of CS for Fun, the CS for Fun magazine, which many of you will have read, has this whole page about computing, computer science and maths and numeracy. Lots of resources there. So there's tons to draw on. And this chap, George Gadanides, who I didn't know until recently, I've given the URL here again, has a lovely slide deck in which he talks about the way in which, through the medium of programming, you get this immediate feedback, and it encourages students to explore mathematical concepts, because that is his goal, teaching mathematics, but to do it playfully and incidentally, in his words here. I love this. You might enjoy the slide deck that's at this URL. I'm just going to take 5 minutes to give two tangible examples, because it's easy to waffle about things like this and just sort of talk high-level aspiration. I'm just going to give you two concrete examples of how I think computing and maths could live together in a symbiotic way. And be cautioned here, I'm not a school teacher, right? This is just my sort of random, I'm just a parasite on this thing. You're the experts, you tell me. But here's some things that go to me. This showed up when I was talking to my 8-year-old son, who was then doing some Scratch programming, and he was having a rocket that was approaching this planet, right? But he wanted it to slow down as it got closer. Well, of course, it might speed up as it gets closer in real life, but he wanted it to slow down. So we talked about x coordinates, and what's the x coordinate of the planet and of the rocket, and if we take the difference between them, that's the distance between them, and then we can make the speed, the number of steps the rocket takes, be a proportion of that, be governed by that distance. And that introduced all sorts of things, right? There's even in writing this tiny program, look, there's one thing that students find difficult in maths is is parentheses to govern the order of evaluation. And here in Scratch, the parentheses have a very visual representation in this expression that you can see. You can talk about scaling and proportion. Here we had to talk about coordinates, and we also had to talk about negative numbers when the rocket was on the other side of the planet. So he was doing negative numbers way ahead, but he wanted them. It wasn't because it was on the curriculum, it's because he needed negative numbers to make his program work, and that's a lovely thing when that happens. It wasn't long before we wanted to move to 2 dimensions, and then we started talking about, maybe we'll move in the x direction and the y direction separately. So it wasn't long before we were talking about vectors as well. I didn't use that language, but he was doing, vector arithmetic, right, in his Scratch program because he needed to, and I loved that. So that's one example, and it can go pretty far, right? You can take examples like this. You can go, inverse square law. You can talk about mass and velocity, and you can talk about 3-body problems. Sorry, typo there. And you can build spreadsheets about this. But the thing I love about it is that it's driven by need, and that it's very exploratory and experimental and playful. It's mathematics made fun. Here's a second example. Which is this is about finding the area of a circle. So if you can teach students the formula for the area of a circle, right? And it's sort of slightly mysterious, maybe, but they'll get to operate it after a bit. But here's an experimental way to do it. Imagine a unit circle drawn around the origin. Then if I threw darts at the unit square, just randomly threw a dart at the unit square, the proportion of the darts that fall inside the unit square is going to be, pi r squared, the area of the circle, divided by 4r squared, the area of the unit square. So maybe I could just try that using a spreadsheet. So here's a spreadsheet in which I've got an x column and a y column, and the formulae in the bottom right, the values are on the top left. For the x and y coordinates, I'm just computing the random numbers between -1 and +1. And then in the inside circle column, I'm computing a Boolean that says whether that xy point is inside the circle. So I need to use Pythagoras for that. And then I've got a formula at the top in cell C1 that is finding what proportion of all the cells in the C column have, say, true, right? Because that proportion is pi. I got to multiply by 4, I think. Yes. Okay, so, and then you can say, well, if I have a few rows, I get a coarse estimate of pi. If I have many rows, I get a finer estimate of pi. And you can, it's not very hard in the spreadsheet to visualize the, where all the darts are landing. So the thing I like about this is that, again, it's very playful and experimental. You can get into quite deep questions like how many experiments do you need to achieve a given position? So you'd be starting to talk about probability by then. We can talk about Booleans as first-class values because that's what lives in column C. And then we don't usually think of a Boolean as a first-class value until we start to do computing. So that's a little computational idea. We can think about, we have to think about Pythagoras. We have a little formula here to take random numbers. There's rand in Excel delivers numbers between 0 and 1. And we wanted numbers between -1 and +1. So we needed little formulas to do that. So there's some mathematical things going on here and some computational things. And it's that, doing both at once that I love. Okay, so that's it. Those are my examples. In my last 5 minutes, I just want to just reflect, perhaps briefly, on some lessons that I think we've drawn from the experience in England, in the hope that they may be of some use to you in Portugal, though I know that education is complicated and every country is different. So your journey will be very different to ours. So I'm not telling you what to do here. I'm just sharing a bit of our experience. So lesson 1, act together. Right. So we had a singular focus, right? A single idea. Computer science is a foundational subject. And it was an educational idea, not just a vocational one. And that speaks to the heart as well as the head. We tried to speak with a single voice, getting everybody on the same side. So we had this CAS as an independent grassroots movements. We got support from professional bodies like the Royal Society and from industry leaders. And so getting everybody on the same side was super important. If governments hear lots of different messages from different people, they don't know what to do. Right? We have to give them a single message because education is hard. And you shouldn't wait for policy change. Just get on with it. And that is exactly what you're doing with your pilot project. So you're doing that already. Lesson 2 for us was build a community of practice. By community of practice, I mean get all those teachers together to talk to each other because they are experts in teaching. So this is grassroots, bottom-up stuff. And the glue, the mechanisms to make that happen were very important to us in practice. So this is the Computing at School network, which incidentally, any of you can join. Just go to search for Computing at School and sign up. You don't have to be in Britain to be a member of Computing at School, and that will give you a little window on a thriving and vibrant community, and you can take ideas from that or contribute to it or take resources from it. Lesson 3, we did this less well. Think about your high-stakes national qualifications. So qualifications drive school behavior. They drive pupil behavior. They drive parent behavior. So if the qualifications are not sending the same message as the curriculum is, then the curriculum might as well not be there. The qualifications are primary, at least they are in England. Maybe it's different in Portugal, but I bet that qualifications play an important role. So I would urge you to pay early attention to looking at your qualifications and making sure that they offer pathways both for the geeks of the future, the software developers of the future, but also for those who are interested, the much larger number who will be interested in applied computing, websites and robotics and data science and so forth, and also everybody else, the future plumbers and cooks and brain surgeons and lawyers of the future, they need digital competence as well. So we need pathways for all of them, and those pathways must lead through qualifications. Lesson 4, pay attention to your teachers. Every time I visit the school where I have the honor to serve as a school governor, I come away awed and humbled by their expertise and by their dedication and by their commitment. One engaged and well-equipped teacher will inspire thousands of students. But being a teacher is hard. It's unremitting. Every day, all those bright, shining faces looking at you. And being a computer teacher is particularly hard because the subject is in flux, because we're making it up as we go along. We don't all know what we're doing here. So but one thing we can do is to love and support and value and and complement and stand alongside our teachers. Let's not do things to them. Let's do things with them and make it clear that they are our partners. In fact, they are our heroes and heroines. Last lesson. Think about computing education research, right? Other countries have, other subjects have centuries of experience in how to teach their subject as a school subject. We have 5 years as a school subject, a bit more as a university subject, but not even much more. So it's kind of madness to spend a lot of money. Like in our country, I think we spend £1 billion a year on teachers' salaries, computing teachers' salaries. It makes sense to spend some money on research to make them more effective in doing their job. And so I would urge the researchers among you to take this seriously, and policymakers among you to think, how could we free up just a bit of money, it doesn't need much, to fund research. So here's my conclusion. So I promised half an hour, and this is half an hour. I think we're as Miguel says, we want to rock the foundations of not only the building you're in, but buildings like this worldwide. We want to make computing a foundational subject that all children study as they do maths and natural science, and in a way that isn't just, boring, dry education stuff that actually brings the subject to life. In fact, that brings mathematics and natural science to life as well. And in particular, as far as mathematics is concerned, I think I'd love to treat computing not as a competition to mathematics, but as a distinctive new way to think about maths education that lets us see maths education in a new light, and maybe even helps maths education to find its true identity. So that's all I have to say. I think there's a few minutes now for questions. I just want to finish by returning to where we began, which with our children. These young people is is the reason for having this conference. I want our children to be engaged and curious. I want them to be empowered and informed. I want them to be creative and playful. And yes, I want them to be employed as well. And I think that reforming computing education will do just that. Thank you so much.